Welcome to this lesson on the gradient. In this lecture, we're going to define the gradient and discuss some of the applications, in particular, how to interpret the direction and magnitude of the gradient vector. So let's start with a definition. Finding the gradient is quite simple. It just requires us to compute some partial derivatives. So the gradient of a function is denoted either by this symbol del of f, or sometimes you'll see grad of f. And it's just a vector, and it's a vector that keeps track of the first order partial derivatives fx and fy in order. So let's look at some examples. If we start with the function fx that we've seen before, x cubed minus 5y squared, then the derivative, or the gradient of f, you can just think about computing the partial f with respect to x, which we know is 3x squared, and the partial f with respect to y, which is minus 10y, and comma separate those. If we look at another example, now we have g of xt is t times e to the x. Then the gradient of g, you take a derivative with respect to the first variable, x, and the derivative there, we know the derivative of e to the x is just itself, and t behaves like a constant, so we get t times e to the x. Next, you take a derivative with respect to the second variable, t, and now e to the x behaves like a constant, so that's just a constant times t. That's a derivative of a linear function, and we just get the constant. If we look at the example for the wind chill function we've investigated a couple times before. We've computed those derivatives before, so I won't go through the details, but this is the derivative with respect to t, and this is the derivative with respect to v, so we just comma separate those to make the gradient. Okay, so let's look a little bit about the graphical interpretation of the gradient. If we look at our wind chill example, and I'm interested in what the gradient is of the wind chill function when temperature is 5 degrees Fahrenheit and wind speed is 25 miles per hour, these are quantities we've computed before, so I'm just indicating those right there, that the derivative with respect to t is 1.33 when temperature is 5 and wind speed is 25, and the derivative with respect to v is negative 0.36. So the gradient at 5 and 25 is simply this vector down here. And if we think about plotting that on the graph, I need to go to the right 1.33 units and down about a third of a unit. So if I move over a little bit here and down here, I can imagine that the vector I'm drawing looks something like that. So one of the things that you'll notice is that vector is kind of pointing straight into one of those contours, and that's not an accident. And we'll say a little bit about interpretation in a moment. But basically what the gradient tells us is that if I'm interested in what direction to travel on my graph to get the greatest rate of change in wind chill, I need to follow the direction of the gradient. So that's what's coming up next. So how do we interpret that? The gradient tells us two things. Because vectors have direction, it tells us which way to travel, and magnitude, there's a length. The direction of the gradient tells us which direction the function is increasing most rapidly, and the magnitude, or the length of that gradient vector, represents the size of that change. So let's just look at a straightforward example. If I've got the function f of xy equals xy squared plus x cubed, and I ask you to compute the gradient at 1, 2 and interpret it. So first of all, it's pretty simple and straightforward to compute that gradient. That's right here. And if I'm interested in that gradient at a particular point, I need to plug in 1 for x and 2 for y, and I should get 7, 4. So what does that mean? It means if I'm standing at the point 1, 2, and I travel 7 units to the right and 4 units up, so I'm at the point 1, 2, and I travel 7 units to the right and 4 units up, so I travel in that direction, which is the direction of the gradient, then the function is increasing at the fastest rate possible. So the direction of the greatest increase of the function is in the direction of the gradient. And sometimes you're interested in what the size of that increase is. So if I just step maybe 1 unit along that path, how much can I expect the function to increase? And that's described by the magnitude of the gradient. And if you haven't done a lot with vectors, magnitude is just the Pythagorean theorem. It's just length. So if I have the vector 7, 4, the way I compute the magnitude, and that's what these bars here are, they describe magnitude, are just the square root of 7 squared plus 4 squared, which is the square root of 65, which is about 8.6. So what does that mean? It means if I travel 1 unit along the gradient vector in that direction, I can expect my function to increase by about 8.06 units. So that's how I would interpret the gradient. Let's look at another example. If we've got a production function and our company is producing some output P, and that's given in tons, and it depends on how many workers we have and the value of the equipment we're using, in units of $25,000. Let's assume the production function is this right here. The production is 5 times the number of workers to the 0.75 times the value of the equipment to the 0.25 power. So let's compute the gradient assuming that the company employs 80 workers, so n equals 80, and has equipment valued around $750,000. And let's interpret that. So I'll let you compute the gradients yourself, but if you do, you should get something like this, just doing some power rules. And if you then plug in 80 and 30, you get this vector. So let's think about what this means. It means if I want to increase production most quickly, obviously we can't have 2.93 workers, but for every approximately 3 workers I add, I should add approximately 2.6 units of equipment value. And if you recall that up here we said that those units were in $25,000 each, that means 2.608 times 25,000, so about $65,200 worth of equipment. So for every 3 workers I add, I should add $65,000 worth of equipment, and that would increase my production value the greatest. If I was interested in what that production value would be, I could essentially compute the length of the gradient, and that would tell me for every single step along that process how much I would increase my production value. Okay, so what I'd like you to reflect on is ask yourself if you can compute a gradient algebraically, if you can interpret the magnitude of the gradient vector and the direction of the gradient vector. All right, thanks for listening.